friend, welcome to this lecture. In this lecture we continue the discussion which we have done in previous lecture. So far we have seen that given a system like x dash equal to say a x, how to find out where A is n cross n matrix, how to find out n linearly independent eigenvector, n linearly independent solutions of this. For this one case 1 is corresponding to the case when we have n distinct eigenvalues of A. So, in this case we have seen that how to find out n linearly independent eigenvectors and hence n linearly independent solutions. And in case 2, when we do not have n distinct eigenvalues of A, and then we have looked the concept of e to power at, and with the help of e to power at into v, we have obtained the remaining or the n linearly independent solution of x dash equal to Ax. And once we have n linearly independent solutions, then we can form your fundamental matrix solution as say x1t to xnt, and we have seen one example where we have calculated fundamental matrix solution. The reason or the benefit of calculating the fundamental matrix solution is that you can write down any general solution as x of t into some constant matrix C. So, it means that where this xt is n cross n and this C is n cross 1 matrix. So, it means that your general solution can be obtained with the help of fundamental matrix solution xt as this, that xt is equal to x of t equal to C, where xt is fundamental matrix solution is C is some constant vector, and with this we are able to find out a general solution. So, now our idea now our say aim is to find out the fundamental matrix solution x of t here, and look at the properties of the fundamental matrix solution. So, now we observe here that the following lemma. Lemma says that a solution matrix xt is a fundamental matrix solution of the differential equation on interval sum I if determinant of x of t is not equal to 0 for all t belongs to I. So, it means that any solution matrix xt will be a fundamental matrix solution provided that determinant of xt has to be non-zero for all t belongs to I. And if you look at the difference between solution matrix and fundamental matrix solution is that in solution matrix the columns are n solutions of your x dash equal to Ax. They may not be linearly independent, but in fundamental matrix solution the solutions, the columns vectors which are solutions of x dash equal to Ax has to be linearly independent solutions of x dash equal to Ax. So, here we say that if determinant of xt is non-zero, then we can say that a solution matrix is a fundamental matrix solution. So, we can prove in this way that if determinant of xt is non-zero for all t belongs to I, then the columns are linearly independent on I, and hence xt is a fundamental matrix solution of 9 on I. So, this we have seen that that x1t to xnt, and if the say determinant is 0, then we can simply say that if we write down C1 to Cn, then if we equate it to 0, then this implies that since determinant of this is non-zero, so this system has only a trivial solution, that is C1 to Cn are simply 0, and this implies that the linear combination, this is nothing but linear combination Ci xi t equal to 0. So, it means that linear combination has only a trivial solution. So, it means that that proves the linearly independentness of these xits. So, it means that if determinant of xt is non-zero, then the linear combination Ci xit can be written as the matrix x into this xt xt into C equal to 0. Now, this determinant is non-zero, so we take the invert of inverse matrix of this, and we can prove that C1 to Cn is nothing but 0 0 0, and hence we can show that these xi t are linearly independent, xit are Li for all I equal to 1, 2 and n. So, it means that, so this is a very easy and important remark, that given a solution matrix, you need to check that if determinant is non-zero for all t, then we simply say that it is a fundamental matrix solution, and we can write our general solution with the help of fundamental matrix solution. Now, here we need to observe one thing, that a matrix may have its determinant ideally equal to 0 on some interval, but still the columns are linearly independent. For example, look at this phi t is 1 0 0 t 2 0 t square t comma 0 here. Then clearly we can see that since it is an upper triangular matrix, so determinant of this matrix is nothing but the product of diagonal term, that is 0. So, here this phi t is 0 for all t between minus infinity to infinity, but still you can say that your columns are linearly independent. I cannot write the third column as linear combination of first two columns. So, it means that columns are linearly independent. In fact, I am if you form this C1 into 1 0 0 plus C2 as T2 0 and C3 as T square T comma 0 equal to 0 0, then the only possibility I have is C1 equal to C2 equal to C3, that is 0. So, it means the columns are linearly independent, but determinant is 0 for all t between minus infinity to infinity. So, it means that this simply says that the columns of the matrix cannot form a solution matrix for the equation x dash equal to a of x. So, if the determinant of phi t is x t is equal to 0 and columns are linearly independent, it means that columns cannot form matrix solution of x dash equal to ATX, because for solutions matrix, if determinant of x t is non-zero, then it is a fundamental matrix solution. And here we have already seen one example, one result. If you remember that here x1 t to xn t, which are solution of x dash equal to Ax, they are linearly independent if and only if that x1 t naught to xn t naught are linearly independent, right. So, if these vectors are linearly independent, then these vectors are also linearly independent, and here we have shown that with the help of the existence and uniqueness theorem, we have proved this result. So, it means that if it is 0 at one point, it has to be 0 for all point, right. So, it means that for this here your columns are arbitrary functions. For arbitrary function, this result may not be true. It means that the previous lemma 4 may not be true for arbitrary functions, but if the columns forms a solution matrix, then of course it has to be true. In fact, we may have one more result, which is commonly known as Abel's lemma, to prove the same thing, that let x t be a solution matrix of 9 on an interval I, then determinant is either 0 or never 0 on an interval. So, it means that once you have a solution matrix, then determinant of x t, if it is 0, then it is 0 for the entire interval. If it is non-zero, then it is non-zero for the entire interval, and this result is known as Abel's lemma. Let us prove it, and once we prove that, then we say that determinant of x t is sufficient to say calculate at any given point in that interval. So, let us prove this small result, and we can prove this by showing that determinant of x t satisfy a scalar differential equation, and solving differential equation we can obtain our result. So, denote the columns x by x1 to xn, and let xj have component x1j to xnj. So, please remember here that each xi, your xj dash is basically a solution of Axj. Now, if you look at the component wise relation, that it is nothing but x1j to xnj equal to A is basically your matrix A11, A12 and so on, A1n and so on, An1 to Ann, and here we have x11, x1j x2j xn j, and this is the derivative here. So, we can find out x dash ij is equal to, now look at the ith column. So, it is ith column is ai say k and xkj, right, and that is what it is written here, that x dash ij equal to summation k equal to 1 to n aik xkj, for ij is running from 1 to n. So, here this is true for all I equal to 1 to n, and j is for each solutions we have this result. So, it means that x dash ij equal to k equal to 1 to n aik xkj is true for all I from 1 to n and for all j from 1 to n. Now, look at the derivative of determinant of x, and determinant of x derivative is nothing but the sum of n determinant. So, in first we differentiate the first row, that is x1 x dash 1 1, x dash 1 2, x dash 1 j and x dash 1 n, and here. So, this is your first column x1, this is second x2, this is x and so on. So, here we need to find out the derivative of determinant of x. Now, let us for simplicity let us write see determinant of x is same as determinant of x transpose. So, let us write down the determinant of x transpose and find out the derivative here, then derivative is also same. So, here I am assuming the first row is your x1, second row is x2 and last row is xn. So, let us find out the derivative of determinant of x as derivative of x transpose, and I am writing derivative of determinant of x transpose is nothing but in the first row you find out the derivative of x1, that is x1 1 dash, x1 2 dash, x1 j dash, x1 dash n, and keeping all n minus 1 rows as it is, plus in second determinant you keep all rows as it is, only the second row is differentiated, right, and in the last element, last term, we have the first n minus 1 rows as it is and the last rows is differentiated, that is x dash n1, x dash n2, x dash nj and x dash nn. So, now this is the expression of determinant of x transpose derivative. Now, use the equation number 12, that x dash ij equal to k equal to 1 to n aik xkj. So, using this for each I, we can write down that x1 1 dash can be written as k equal to 1 to n a1 k xk1, and similarly x1 2 dash can be written as k equal to 1 to n a1 k xk2. You can look at here, this is x1 1 dash and this is x1 2 dash, and you look at this 1 is written here, 2 is written here, and this is x1 n dash. So, we have written the expression of x1 1 dash, x1 2 dash, x1 n dash, and similarly we can write down in second term the expression for x2 1 dash, x2 2 dash and so on, and we return the corresponding expression in terms of say a differential equation. So, using 12 we can change the first row as this, second row, and similarly nth row like this. Now, here if you look focus on the first row, then you can simply say that I can simplify this from the first row, we say subtract the second term multiply by a12, last term by multiply by a1n, and when you simplify and when we subtract, then determinant will be unchanged, and it is in the first row you will get a11 x. So, here you will get that a11 and the determinant of x, and in second component we will do the same thing and we will get a22 determinant of a22 will be taken out from each term, and we can write down this second component as a22 determinant of x. Similarly, the last term can be written as ann determinant of x. You can look at it in this way. When you simplify for k equal to 1, so let me write it here one term. Okay. So, here this is what it is written as an1 x 1n plus an2 x n x2n and so on a n n x n n. Now, this x n a n 1 x 1 n is basically say multiple of this component multiplied by a n 1. Similarly, this is nothing but a n 2 multiplied by this term. So, here what you can do, you write R n as R n minus a n 1 R 1 minus a n 2 R 2 and so on minus a n n minus 1 R n minus 1. When you do this, then only this term left, rest all terms are simply gone. So, this is written as a n n x n 1, this is a n n x n 2 and here it is a n n x n n. So, now if you take a n n common from the last row, then it is nothing but a n n and the remaining is nothing but the expression of determinant of x transpose, right, and that is what I have written here. And since determinant of x transpose is same as determinant of x, we have written this as a n n determinant of x. So, here we write determinant of x dash is equal to a 1 1 determinant of x plus a 2 2 determinant of x and so on, and we can write this if we simply sum this, then we have determinant of x dash equal to k equal to 1 a k k t determinant of x. If you look at this is nothing but the trace of the matrix A. So, trace of the matrix A. So, it means that determinant of x dash equal to trace of A into determinant of x, and if you look at this is nothing but say first order differential equation, and we can find out the solution as this thing that x of t equal to x of t naught into e to power this exponential of this say trace of a t a into this t minus t naught, right, and here you can simply say that t naught is any initial point in the interval I. So, if x t naught is 0, then x t will be 0 for all t, and if x t naught is non-zero, then x t will be non-zero for all t. So, this will give you that it will be 0 throughout or never 0 on the entire interval. So, it says that rather than checking that determinant of x t is non-zero for all t, it is easy to check the determinant of x t at a given point, and it will remain non-zero for all time t. So, we can reformulate our previous lemma, and we write the lemma 4 as this: a solution matrix x t is a fundamental matrix solution of the differential equation on an interval I if and only if determinant of x t naught is not equal to 0, where t naught is an arbitrary point of the interval I that we have shown here. Okay, so, we can write so now onward whenever we want to check that it is a fundamental matrix, we will check only at one point, otherwise not. Okay. So, this is please try to understand, this is true for solution matrix, not for any matrix. Okay. Now, let us look at one example, and we show that x t equal to t square t 2 t 1 is a fundamental matrix for the system x dash equal to a t x, where a t is this matrix 0 1 minus 2 by t square 2 comma t on any interval I which is not containing the origin. The reason is that if it contain the t equal to 0 point, then a t may not be defined. So, to define the matrix A t, we exclude the point t equal to 0 from the interval I. And in the second part, we can easily see that if you look at the determinant of x of t, this will be 0 at 0, and we try to see whether it will say create some kind of problem to the previous result. But let us assume that we have obtained the solution matrix as x of t as t square t 2 t and 1, and here since the interval I is not containing point t equal to 0. So, here this determinant of x 0 equal to 0 will not create any problem to the previous result, that is xt is a fundamental matrix if and only if determinant of x t naught equal to 0, because t naught is an interior point of this interval I, and here the 0 is not belonging to this interval. So, here the only remaining part we have to show is that we have to show that x t equal to t square comma t 2 t 1 is a fundamental matrix solution of the matrix of the differential equation x dash equal to a t x. So, let us solve this, and we write here that let x equal to x 1 comma x 1 x 2, and we can write down our system of linear equation x and in the following form x dash equal to a t x. And since here we have not discussed, and in fact it is very difficult to handle the non-autonomous case. So, here in this particular case we can solve this, we can find out two linearly independent solution by converting this into a second order linear differential equation. So, we are trying to convert this into a second order linear differential equation. So, for that if we look at x as x 1 x 2, then I can write x 1 dash equal to x 2 and x 2 dash equal to minus 2 upon t square x 1 plus 2 by t x 2. So, using the value of x 2 as x 1 dash, we can put it here, and we can write down this as t square x 1 double dash plus minus 2 t x 1 dash plus 2 x 1 equal to 0. So, here we can write down the expression for x 2, and we can write this as x 1 double dash equal to minus 2 by t square x 1 plus 2 by t and x 2 as x 1 dash. So, when you simplify, you will get this t square x 1 double dash minus 2 t x 1 dash plus 2 x 1 equal to 0, and if you look at, observe that this is nothing but a Cauchy-Euler equation of the second order. So, in Cauchy-Euler equation we assume that t to the power r is a solution of this, where r you need to find out. So, assume that x 1 equal to t to the power r is one solution, then we can put it here as a solution here. So, we will get what, r into r minus 1 minus 2 t r 2 r plus 2 into t to the power r equal to 0. Now, t to the power r is non-zero for this t not in the interval which is not containing 0. So, it means that this has to be 0, and if you simplify, it is r square minus r minus 2r plus 2, and this is r square minus 3r plus 2 equal to 0, and we can simply say that it is r minus 1 into r minus 2 equal to 0. So, we can find out the roots of this equation, which is known as initial equation, and roots are written as r equal to 1 and r equal to 2. So, it means the solution of this Cauchy-Euler equation is given as this t square, and second solution is given as t. Now, corresponding to r equal to 1, we have x 1 2 as t, and corresponding to r equal to 2, we have solution like this. But we need to find out the solution of the system, not for this Cauchy-Euler equation. So, here solution of the system is x 1 x 2. So, x 1 x 2 is basically y, and sorry, let me use it here. It is x 1 is okay, x 1 x 2 is x 1 dash. So, it is x 1 here, let me write it here. So, it is x 1 and it is x 1 dash. So, x 1 we already know, if we take x 1 as t square, then your x 2 is going to be 2 t, and if you take x 1 t as t, then your x 2 is going to be 1. So, it means that two linearly independent solutions are t square 2 t as one solution, another solution is t and 1, and you can see that these are linearly independent solution. And how we can check? You write C1 plus C2 equal to 0 0, and this is true for all t in this interval I. So, in particular, take some value of t in this interval, and you can verify that C1 and C2 are linearly independent. Or you can simply say that I cannot write t square 2t as combination of as constant multiple of t into 1. If you look at this, let me simplify this, and let us say that if C1 and or C2 are non-zero, at least one of them is non-zero, then I can divide by that. So, I can write t square 2t as constant multiple of T1, but you can see that this cannot be true because T square cannot be written as constant multiple of T. So, it means that here C1 and C2 has to be 0. So, it means that this solution T square 2T and T1 both are linearly independent solution, and we can find out the matrix solution XT as T square 2T and T1, and since we have already seen that these are linearly independent, so we can call these as fundamental matrix solution. So, in case of time non-autonomous system, we have very limited option to find out the linearly independent solution, but in this case it is boiled down to very simple problem, that is Cauchy-Euler, solving a Cauchy-Euler equation, and in this case we can find out the fundamental matrix solution as follows. Let us move further and let us look at that for autonomous system of linear equation we have the following result. Basically now we are trying to characterize the fundamental matrix solutions. So, this lemma says that a matrix XT is a fundamental matrix solution of X dash equal to Ax if and only if X dash T equal to Axt and determinant of X0 is not equal to 0. So, here in case of non-autonomous we have to look at the interval, but in case of autonomous we can work for the entire T in R. So, here we need not to mention any interval here. So, here we simply write we want to show that any matrix XT is a fundamental matrix solution of X dash equal to Ax provided it satisfies the two properties. One is that it is satisfying X dash T equal to Axt, and second is that determinant of X0 is non-zero. So, let us prove this simpler result. So, let Xi denote the n columns of XT. It means that your XT is written as x1 t and so on xn t. Then we can find out the derivative as x1 dash t x1 xn dash t. Please observe here, finding the derivative of a matrix and finding the derivative of a determinant are two different things. In derivative of determinant you have to write this as a sum of n determinant, and in each sum you are finding the derivative of one row, but in case of matrix derivative of the matrix is nothing but derivative of each row at a time. So, here x1 dash is equal to x1 dash t to xn dash t. Now, Axt is given as, I can write Axt is equal to Ax1 t as a first column, Axn t as a nth column, and since these two matrices are equal, so we can say that Xi dash equal to Axit. So, it means that the system X dash equal to Axt and this n system of linear equation Xi dash equal to Axit are equivalent. So, it means that saying that X dash equal to Axt, where Xt is this, is equivalent to show that each column Xi t satisfy is a solution of this system Xi dash t equal to Axit. So, it means that the first condition is nothing but to show that the columns of the matrix Xt is are solutions of X dash t equal to Axt. Now, so it means that first condition is nothing but to show that it is a solution matrix. Now, second is what? Second we want to show that it is nothing but showing that columns are linearly independent. So, here n solution x1 t to xn t of x dash equal to Ax are linearly independent if and only if the solution evaluated at any given point are linearly independent vectors, that we have already proved, and it can be proved further with the help of Abel's lemma. So, it means that you can evaluate at t equal to 0 and you can see that x1 0, x2 0, xn 0 are linearly independent, and hence this implies that determinant of x at 0 is non-zero, right. So, this shows that this xt, any matrix xt is a fundamental matrix solution. Here the size of xt is n cross n. So, any matrix of size n cross n is a fundamental matrix solution of x dash equal to Ax provided that it satisfies this equation x dash t equal to Axt and determinant of x0 equal to non-zero. So, please look at the difference between this x dash t equal to Axt and x dash t equal to axt. Please look at the difference here. Here it is n cross n, it is n cross n, it is n cross n, and here it is n cross 1, n cross n, n cross 1. So, here it is a matrix differential equation, and here we have a system of differential equation. So, this is the only difference. Okay. So, fundamental matrix will satisfy this matrix equation, matrix differential equation. Now, with the help of this, now we try to prove that matrix valued function e to power at is a fundamental matrix solution of x dash equal to ax. So, to prove this, we simply observe two things. The first thing is that e to power at, since it is written as this, then we can easily check that derivative of e to power at is nothing but a e to power at. So, it means that it satisfies this equation x dash t equal to a of x t. Now, second thing we need to prove that determinant of x0. So, determinant of a into 0 is nothing but identity. So, determinant of identity is nothing but 1, which is non-zero. So, hence we can show that e to power at satisfy the condition given in the previous lemma, that is e to power at is a solution of x dash t equal to axt, and determinant of e at evaluated at t equal to 0 is non-zero. So, hence we can say that e to power at is a fundamental matrix solution of x dash equal to a of x. So, we have proved that the matrix valued function e to power at is a fundamental matrix solution of x dash equal to ax, and as we have pointed out earlier also that there may be more than one fundamental matrix solution. So, now we try to see that if there are more than one linearly more than one fundamental matrix solution, what are the relation between these fundamental matrix solution, and that is the content of the next lemma. It says that if x t is a fundamental matrix solution for linear system x dash equal to ax on some interval I, and C is any non-singular constant matrix, then x t into C is also a fundamental matrix. So, it means that given a fundamental matrix, you can find out another fundamental matrix by multiplying by any non-singular constant matrix C. So, it means that once we know one, we have infinitely many. Also, in a reverse conversely, we can show that if y t be another fundamental matrix solution, then it is also can be written as the form of x t into C for some non-singular matrix C. So, idea is what, that if we have x t, then x t C will also be a fundamental matrix, and if we have some other matrix y t fundamental matrix solution, then we can find out a suitable non-singular matrix C such that y t can be written as x t into C, right. So, it means that any two fundamental matrix are unique up to a multiplication of a non-singular matrix C. Now, here please observe, we are writing x t into C, we are not writing C into x t. You may observe that this may not gives you the fundamental matrix solution. So, this I am leaving it to as a homework for you. So, now we will focus on this, that if x t is a fundamental, let us try to prove this lemma 10. So, if x t is a fundamental matrix solution, then x dash equal to ax, it will satisfy this x dash equal to a of x. Then we can verify that x of C will also satisfy the same matrix solution, matrix equation, that is x c dash, if you calculate, it is nothing but what, x of C dash is equal to x dash C, because C is not a C is a constant matrix. So, we can write x C dash equal to x dash C, and x dash we already know that it is a of x. So, we can write a x C, and this is nothing but a times x of C. So, it means that x C will also satisfy the system x dash equal to a of x. Now, we can check whether, so it means that first thing is obvious, that it is a solution matrix, so that x of C is also a solution matrix. Now, second thing we have to show that determinant of x of C is non-zero. So, determinant of x of C is nothing but determinant of x into determinant of C. Now, determinant of x is non-zero because x is a fundamental matrix solution, and determinant of C is non-zero because C is a non-singular matrix which we have taken as a non-singular matrix. So, determinant of XC is also non-zero. So, it means that XC will also act as a fundamental matrix solution. So, we can say that if X is a fundamental matrix solution and C is a non-singular matrix, then X into C is also a fundamental matrix solution. So, this proves the first part. Now, we try to prove the second part, that any fundamental matrix solution can be written as XT into C, where C is some suitable non-singular matrix C. So, now let us prove this. Now, since XT and YT both are fundamental matrix solution on I, and if you look at the XT is fundamental, means determinant of XT is non-zero and determinant of YT is also non-zero. So, it means that columns of XT and columns of YT forms n linearly independent solutions, and hence they will generate they will act as a basis of the solution space of x dash equal to Ax. So, it means that any solution can be written as columns of y, and any solution can be written as linear combination of columns of x. So, using this let us find out the matrix C which we wanted to know. So, let Xj is a solution where Xj is a column of a jth column of the fundamental matrix Xt. So, Xg is a solution and columns of y forms a set of n linearly independent solution of 9, or we can say the columns of y forms a basis of solution set of x dash equal to Ax. So, we can write Xj as linear combination of yi's. So, I can write Xj equal to I equal to 1 to n Cij yi, and we can write this as y of Cj, where y is your this y1 to yn, and this Cj is nothing but C1j to Cnj, okay, where Cj is given as C1j to Cnj. So, it means that we can write that x of t as y of t equal to C, where C is the column C is the matrix whose columns are these Cj's. So, it means that I can write x of t as yt into C here. Now, xt is fundamental, so determinant of xt is non-zero, yt is fundamental, so determinant of yt is non-zero. So, we can show that determinant of C has to be non-zero. So, it means that determinant of C is non-zero. So, it means that C is a non-singular matrix, and any fundamental matrix yt can be written as in this form xt equal to C, where C you can obtain with the help of xt and yt. Is it okay? So, this says that any two fundamental matrix solutions are related like this, that yt can be written as this, and this is a very important observation, and with the help of this observation we will try to obtain the expression of e to power at, and once you know e to power at, you can write down any solution in the form of e to power at. So, but that we will do in next class. So, here we stop, and we will continue in next lecture from this onward. Thank you very much for listening us. Thank you.